Back, everybody, and today we're going to pretty much finish up this chapter as we take a look at chi-squares. Now, we're still in hypothesis testing, so we're going to take a look at how chi-squares interface with hypothesis testing to give us more in-depth analysis of our data. Well, welcome back, everybody, and today we are still in chapter 21, and today we're going to be looking at the chi-square test for goodness of fit. Now, I'm taking these formulas one at a time because several formulas of these types of formulas, as complex as they are, it may overwhelm you. So we are nearing the end of the course, so I want to get these models out, or these formulas out, just to expose you to them. And we have maybe one or two more that we may get into, and we will finish out the course. But today we're going to be looking specifically at chi-square. Chi-square is not very difficult to understand, so let's go ahead and go with the topic of the chi-square today. Now, what is it? It's a test of statistical significance, as we saw, and as you see, it is appropriate for testing hypotheses about frequencies arranged in a frequency or a contingency table. Now, I have included in your Moodle shell for this week both a t-test table and a chi-square table. The authors here talk about the appendix, and each chapter ends with an appendix, but I cannot find these tables. It may be that they're hidden somewhere, or I'm just overlooking them. So what I did was go through and find a chi-square table and a t-test table so that you can get an idea of how to look for these if you ever do these outside of class. But here, when you're looking at chi-square, you are looking at data that are derived from nominal and ordinal variables, and we examine those variables with the chi-square test. But now also, what we're looking at as well is goodness of fit. And again, I want you to use your textbook. We're on page 521, and what the goodness of fit can be thought of is how well some matrix or table, which is what I provided for you, of numbers matches or fits another matrix or table of the same size. And it's usually, as you see here, between a table of frequency counts, which is what I've given you from the internet, observed in the sample data, and another table of expected values, which are the central tendencies for those counts. Now, what does all of this mean? Well, as you can see here, we have a hypothesis that they give us an example of, and it's Papa John's Pizza stores are more likely to be located in a standalone location than in a shopping center. So now, and the way that it's introduced is, let's say, for instance, you are a mom and pop pizza store, and you're thinking about opening up a pizza store, but you don't know whether to have a pizza store in a shopping center, or if you can be better off having it as a standalone. Well, one of your major competitors, of course, will be Papa John's. And so the relative usefulness of a chi-square is to be able to determine what is the competition doing and where are they most likely to be located. Because as a marketer, you want to make sure that you've got less competition than you can take. So this is how we would use that chi-square. So, and if we go down here with the little table on page 521, we can see here that we have observations. The standalone is 60 stores. Shopping center is 40 stores. And the total is going to be 100 stores. Simple math so far. And I'm just going to read it as we go along. These observed values, which you can see here, is O I can be compared to the expected values for the distribution, which is EI, to complete a chi-square test. A chi-square value will reflect the likelihood that the observed values come from a distribution reflected by the expected values. So the higher the value of the chi-square test, the less likely it is that the expected and observed values are the same. Now, as I say here, computing a chi-square test is fairly straightforward and easy. And if you master this, you should be good in understanding other future significance tests, because the basic logic of the chi-square test underpins all the rest of this. So, as you see here, there are steps in computing a chi-square test. Gather data, tally the observed frequencies for the categorical variable, and we looked at that when we saw gathering data and putting it into some type of meaningful order, and then compute the expected values for each value. Calculate the chi-square value using the observed frequencies from the sample and the expected frequencies. Find the degree of freedom for the test. Make the statistical decision by comparing the p-value associated with the calculated x-square against the predetermined significance level, which is the acceptable type 1 error rate. Now, this is how we see it being played out. We have here the data for the location variable, standalone or shopping center, which is right here, are provided in the frequency tables. The next step, what are the expected frequencies for the location variable? This is another way of asking the central tendency for each category, or how the observations would be distributed if there was no relationship between the categories and numbers of stores. Now, since the sample size is 100 and we're dealing with 2 categories, finding the expected values should be easy. If no pattern exists, now this is the important part, if no pattern exists in the locations, they should be distributed randomly and evenly across the 2 categories. So here's what we would expect. This is where you see the 100. We would divide it by 2. So we have both 50 in each cell or each variable, and that would lead us to 100 stores. And you see that here in the little table on page 522. Now, here's how you compute the chi-square. Okay? The chi-square formula is equal to the sum of the observed frequency minus the expected frequency squared divided by the expected frequency. And when we take a look at it, we have, for this one, we've gone over, you see standalone, we thought it would, because of the randomness of it and because we weren't sure of the distribution, we both gave it equal values here in the expected frequencies, but the observed frequencies was 60 and 40. So you had a plus 10 here and a minus 10 here, and it cancels out to 0 here. The way that we go about the chi-square formula is to take 100 divided by 50 is equal to 2. 100 divided by 50 is equal to 2. And the chi-square value is equal to 4 here. Now, on page 523, they give you this formula, or they give you the same thing that you're looking at here. But also, you have to consider, like many other probability distributions, the chi-square distribution is not a single probability curve, but a family of curves. Now, these curves vary slightly with the degrees of freedom. In this case, the degree of freedom can be computed as k minus 1. And that's the number of cells. We have 1, 2. And so if we take the number of cells minus 1, we would have 1. Let me see if it's on this one here. No, I don't see it. But what we have here, if you take a look here at the bottom of 523, you see here that the degree of freedom is equal to 1. Now, the computed chi-square value needs to be compared with the critical chi-square value associated with 0.05. That's at 95% probability level with 1 degree of freedom. Now, they say in table A4, I couldn't find it, of the appendix, the critical chi-square value is 3.84. Now, I want you to go into Moodle and you see where I've given you the chi-square table. Go look that up and just to see where it lands on the table, and you'll see the same thing. Now, since the calculated chi-square value is larger, and we see here the chi-square value is 4, but the critical value in the table is 3.84, so it is larger than the chi-square table. And the conclusion because of that is that the observed values do not equal the expected values. Therefore, the hypothesis is supported. More Papa John restaurants are located in standalone locations. Now, really, personally, you can see that by the observed frequencies. You see the standalone is 60, shopping centers are 40. But the chi-square, I guess, validates or confirms what you have already seen. So it's nothing that is going to really illuminate or give you more insight. It is a way of testing the hypothesis. And again, really, when you think about it, it's the way that we test and verify the statistical significance of our data that we're looking at. So chi-squares, and the next chapter deals with chi-squares as well. We'll be looking at that, but it's enough today to understand just the basics of a chi-square, and I'll give you another project, a fairly easy project, which involves looking up a chi-square value based on a degree of frequency like you did with the t-test yesterday, and that will be your forum question for today. There's not a whole lot we can do to embellish on statistics. They are what they are. And the examples that you have in the book, they're just as relevant as anything else that I could come up with. And you having the book, because we are primarily online now, is to be able to give you the things that you have ready access to. But you might want to take some examples from online resources and even in the textbook and test your skills with the chi-square and also the t-test and hone in that. A lot of times, I've said I'll never use this again, and when I took statistics, when I finished that course, I didn't think I would ever see statistics again. I swore up and down I would get away from it. But look at me now, I'm teaching this stuff. So that's the chi-square. We'll move on tomorrow to another area in chapter 22. So until then, have a good day, and we'll come back tomorrow. Today we took a look at chi-square testing and goodness of fit. Now next time we're going to be looking tomorrow at bivariate hypothesis testing. So take all this stuff in, take good notes, and we will see you tomorrow.